witness Michele Silverstein defending. Michele joined us as an undergraduate from Cornell University, a place near and dear to my heart. And what you didn't realize probably is that 40% of the city went to Cornell. Because Brian was a grad there and I was an undergrad. All good and with house. I'd also like to be sure to welcome Sheila and David, Michelle's parents who are here, who came down from New Jersey, and Brian Berg is here for emotional. Michelle's +1, and I think you.
Very important. Along with Elliot.
And it's interesting timing for today's defense, because 5 years ago, the first day that Michele and I ever observed at the .9-meter telescope in Chile. And this is the moment when Michele became known as the because that night and the subsequent nights after that, more things went wrong with that telescope. I had not seen these problems before. I had not seen them. This included things like the dome would not close, the windscreen would not go up, the platform would not go down, the lamps would not come on. It was an amazing series of chaotic events, and Michele took it all in stride. We had a major snowstorm, we had a lot of good pictures, we had a lot of fun on the mountain, we even got some sun. So I figure if Michele can survive that observing run, she can survive just about anything. And one of the things she taught me how to do, in fact, was part of her survival techniques. She helped me break this plate.
Oh my God.
By punching it. And I have gone, ever since that time, I've never punched Michele and she's never punched me. So I think that's pretty good, actually. And without further ado, Michelle's going to tell us all about reducing the chaos amongst red dwarfs and telling us what it's really all about.
Thanks, Todd. That was pretty awesome. All right, so I'm going to tell you about my project, Sizing Up Red Dwarfs in the Solar Neighborhood. I've been studying the nearest, smallest stars, and I've been figuring out how large they are and using that to figure out a variety of properties of these stars. First, I'd like to make some acknowledgments. So thank you to my committee for being here and reading my dissertation. Especially Todd, my advisor, Sebastian Lapine, Andrew Mann, who's here from North Carolina, Brian Toms from the physics side of the department, and Russell White. I also want to thank the Recons team. This is pretty much everyone I hope I've overlapped with over the years, and you've all been super great and made it awesome to work on these nearby stars and help me with various projects or just, feeling like I could do things, and thanks so much. Also, I'd like to thank Crystal, Ryan, Katie, and Tiffany, who have also been there through it all, and so it's really nice to have such great co-grad students. And all the grad students throughout the years, because you've made it really a nice place to be. So thank you guys. And finally, I'd like to thank my parents for coming all the way out here and being supportive and everything. And my boyfriend, Brian, for keeping me and the apartment together. And Brian's parents, who've made me feel like part of the family. It's really, really nice. So thank you all for all the great things you've done.
That was a great talk.
Oh, yes. Anyway, so now we have to talk about science. We should do that. All right, so I'm going to be talking about red dwarfs. I've told you, so these are the smallest, coldest stars. Why do we care about them? They make up the majority of stars in the solar neighborhood, and they are host to small planets. Also, because they're so faint, they're often difficult to study and therefore neglected in a lot of work. Also, with the coming TESS mission, we are going to be seeing a lot of results for these stars in terms of both how they vary with time due to magnetic activity and because of planets passing in front of them. So they are a hot topic. Also, our nearest neighbor is a red dwarf, Proxima Centauri, and it in fact has a small planet about 1.3 times the size of the Earth. So even our nearest neighbor is doing cool planet stuff. What do we care about the size of the stars? Well, it turns out if you're getting a planet from TESS, you're finding a transiting planet, in which case you need the size of the star to figure out the size of the planet. If you have a bunch of these, you can figure out the like the demographics, what kinds of systems are you finding and how often? Then you can use that information to learn something about how planets form. You also need planet radius if you're going to find Earth-like planets, which is, again, something a lot of people are pretty excited to do. You can also use stellar radius to figure out the size of a planet, the age of a star. So a young star is still contracting out of the main sequence, so you'd expect it to be a bit larger. And subdwarfs are smaller than the main sequence because they have lower opacity, and so there's less push from radiation pressure to keep it inflated as much as main sequence stars. So if you find a bunch of these stars, you can isolate different stellar populations, which in turn teach you about galaxy evolution and star and planet formation if you have enough of them. Another thing that could cause a large stellar radius is if there's magnetic activity. So if you find these stars and you figure out it's related to magnetic activity, you can learn a bit more about stellar physics. If you combine these three things together, you can actually learn about how stars affect their planets over time, which is something I find pretty cool. But for this talk, we're going to be focusing on the radius of the stars and different aged planets, stars. I'm not at planets yet. That's the next job. All right. So what do we actually want to do in particular? So I want to identify different stellar populations. I want to find young stars. I want to find old stars. And I want to figure out who's who. I also want to look for trends in the characteristics of these red dwarfs. And I'd like to get the best radii possible so that when we actually find the transiting planets, we can get really good exoplanet radii. So to do this, I need to get the radii. So I need to make a method. Ideally, it is automated, uniform, accurate, inexpensive, and efficient. Lots of things. Very ambitious, I think. And then I want to use the method to make a catalog of these parameters. And for this project, I've looked at 1,400 red dwarf primaries within 25 parsecs, and an additional, including 100 young stars within 25 and out to 50 parsecs, and subdwarfs, young stars and subdwarfs. All right, so how do we make the sample? So first of all, what is a red dwarf? So for our work, we're claiming a red dwarf to be any star from M0 to the end of the main sequence. And we prefer to define this according to the V minus K color because it spans the largest wavelength range that you can observe from the ground and therefore spans the largest possible portion of the spectrum. So the final range for this study is a V minus K of 3.5 to 10.5. Any star in that range qualifies, almost every star. And I'm going to gloss over the details of that so that I can actually finish the talk. But the 3.5 cutoff comes from a comparison of spectral types to V minus K from the PMSU survey, Richard Gray, and Recon's work for spectral types. We compare those spectral types to the V and K magnitudes to make a cutoff. The 10.5 value comes from Diederich et al., who studied the smallest star, and we used values based on that to come up with this cutoff. So our stars come from the Recon's 25 parsec database. Big surprise. The database contains astrometric, photometric, spectroscopic, and multiplicity information for all of the stars within 25 parsecs. These are the key people who've been working on this database for a long time. So we get pretty much all of our main sequence stars come from this database. But we have Wei Chun, who tells us which stars are subdwarfs, and Adric Riedel, who tells us which stars are young stars. And in fact, I've actually been able to add subdwarfs and young stars out to 50 parsecs because of their work. Otherwise, I wouldn't have enough stars to do any meaningful comparison. And then Jen Winters has wonderfully provided multiplicity information. That's been her, that was her PhD work and now also her postdoctoral work in part, so that I can make sure that data for what I think is a single star isn't contaminated by another star that I didn't know was there. So what do I actually want in the project? So I've said, of course, the main sequence stars, the young stars, subdwarfs. I only want main sequence primaries, or I only want stellar primaries. I want stars across the entire sky, and I don't want any companion within 4 arcseconds because that's the resolution of 2MASS. And we need that data, so we want it to be not contaminated. And again, we want main sequence stars within 25 parsecs, young stars and subdwarfs within 50. So we're left with 1,437 main sequence stars, including Proxima Centauri, even though it's not a primary, because it's the nearest star. And we have 52 young stars and 35 subdwarfs. So we have our sample. Let's talk about the data. So for the procedure I'm going to talk about, I require optical, near-infrared, and mid-infrared photometry. So I'm getting Johnson-Krohn-Cousins VRI, 2-mass JHK, and Wise W1, 2, and 3. So our optical data comes from the CTIO 0.9 meter, the ArcSat 0.5 meter, and the WIN 0.9 meter. Of course, we have also then 2-mass and the WISE survey. We're also going to require parallaxes and, again, companion information. And as I mentioned, these come from the 25 parsec database. So a little bit more about these telescopes, because I did a lot of going to telescopes, as some of you may know. So if you look at, okay, we have the telescope, we have where it is, we have the instrument, we have the number of nights I used the telescope, the number of nights I acquired the data I need for the project, and the number of stars that I actually reduced data for. So I've actually done like more than 6 months of observing. So almost 10% of my time here has been using a telescope. And I thought that deserved a slide. So here we are. Also, I was the SMARTS graduate fellow, so I was responsible for maintaining all the data coming from the SMARTS 0.9 meter for recons and reducing all of the photometry that came in. And so we have a giant number here of stars that I actually reduced data for. Not all of that was for the project, but pretty much all of these from the other 2 telescopes are for my project. All right, so one telescope at a time. Oh, no. All right, one telescope at a time. So I just wanted to point out what they are. So we've got the 0.9 meter in the southern hemisphere. Again, I got lots of stars for that, data from that. But of course, that's only the southern sky. Remember, this is an all-sky survey. So we looked to ArcSat next, and Tiffany and I did a lot of observing together. We kind of overlapped in our programs. So she would do some of my stuff, and I'd do some of her stuff. And it was really nice because I didn't have to go anywhere, so that was cool. Although there are a few people who may know that ArcSat is not perfect. So one of the things that were unfortunately not perfect is that it was small. So it was taking a long time to do everything. So I applied for NOAO time at the WIN 0.9 meter, and that made things go a lot faster. So what was I doing at these telescopes? Well, so the idea here is I'm going to get images in 3 different filters for all the stars I want to study, right? So then I also need to calibrate those stars, so like known values. Otherwise, it's just like the telescope says it's this bright, but it's not part of any, calibrated system. So I have to observe both what I'm calling science stars, which are the stars I want to learn about, and standard stars, which are used for those calibrations. And I want to measure those standard stars across a variety of altitudes to account for atmospheric effects. And I also want to look at some of the science stars that already have data, so that when I go later and I look at the data, I can say, okay, these match known values from before, so probably all the stars are also, all the other stars without previous data are probably okay. Also, of course, the sky cannot have clouds for this kind of measurement. So this is what a raw frame looks like from the 0.9 meter. First step is going to be, as I'm going through the processing of these images, to calibrate the image. And then when I'm going star by star, I plop a little 7 arcsecond aperture around it, and I count up all the photons. And then I subtract the sky background. And I do this for all the different standards. And then I apply the calculation I get to calibrate to all the other stars as I do the same thing to them. So I just want to show you the 3 different telescopes. We've got a raw frame on the left and a processed frame on the right. So this is from the 0.9 meter. You can see the little dust motes that go away when I process the image. We have ArcSat, and we have the WIN 0.9 meter, which is a little different because of the way the images read out. So you have 4 different images. So I do the same thing I did before, but then I have to stitch the image together. And there's this vignetting effect over here because the filters were too small for the filter wheel. But I don't have to, it doesn't actually affect any of my data, so I just kind of leave it because being efficient. All right. So now we have the data, we have the sample. Let's get some radii. So the main idea is that if we have a variety of filters, we can make a bunch of different color combinations. And we can compare those color combinations to model colors that we extract from a model spectrum. And that can help us figure out what the parameters are of the star across a large wavelength range. I have a picture of Serge here because he did the original version of this method. And some upgrades since then include that I have an automated method, whereas Serge actually picked colors by hand and looks for weird stuff and will get rid of it by hand. I don't do that because I have a lot more stars and it'd be really tough. I also use a different filter set, and I look at hotter stars. It's a little bit about the spectra that we're going to be using. So the models are a pre-made set of spectra that correspond to 4 different parameters. We have temperature, metallicity, surface gravity, and alpha enhancement. And they go in intervals of 100 Kelvin, 0.5 dex, 0.5, and 0.2 dex. These are the highest quality models for low mass stars, as recently as in 2018. There are new versions of the BT saddle models, but they don't go a different, they're constrained to metallicity 0, which, I mean, they can generate the code to have more different metallicities, but I have to talk to them and still work that out. So here's what a spectrum looks like. There's like a ridiculous amount of detail, so it looks kind of blocky. And I also have we have flux on the y-axis and wavelength on the x-axis, and these vertical lines are my VRI, JHK, YS1 and 2 filters. So they're effective wavelengths to give you a sense of what I'm actually extracting from the spectrum when I get the model colors. So they're the actual filter traces. And if you really want to see W3, it's like way over there. All right. So now you have the model. So how are we getting, for example, temperature? So we're going to use all the model colors and the observed colors, and we're going to do a least squared comparison to get the best fit. So this is sort of in brief. Then we're going to get bolometric flux. Once we have to do this, we're going to take the best fitting model spectrum from the temperature step. We're actually going to have to wiggle it a little. Apparently, low mass stars are very hard to model, so models are not perfect. And I consulted with the creators, and they said this is OK. So that's what we're going to do to match until we match observations to within 0.03 magnitudes. And then we're going to integrate the modified spectrum across the wavelength range of our filters, and then apply a bolometric correction so that we've got the full bolometric flux. Once we have that, we scale the flux using parallax to get bolometric luminosity. That leaves us with temperature and luminosity, which we can combine using the Stefan-Boltzmann law to get radiance. So again, I've said this a few times, we're combining a bunch of colors. We have a lot of colors that we could use with all the 9 bands. But can we use them all? Are they all useful? So to test that, I went through the temperature procedure, which I'll talk about more. And each color gives you a temperature, right? And ideally, all the colors would tell you the same temperature, and you'd be like, OK, this is the answer. But they don't. And so if you take a median, you can figure out how far each color goes from the median. And if there's a color that's like way off all the time, you don't want to use it. So what I have here is, so I have all the different colors. They're in the different plots. So we got V minus R, V minus I, V minus J, and so on. And down here we have, start going into infrared minus infrared. And on the y-axis, so I know it's like tiny font, it goes from 0 to 400 Kelvin on the y-axis. And on the x-axis, we have 3.5 to 10.5. So in each plot, the left side are the warmer stars, and the right side are the cooler stars. So if for the points, so there's about 200-something stars in here. The points that are frequently above 0 are frequently far away from the median. So right away, we can see we can see that there's sort of a difference on the left and right sides of the plot. There seem to be 2 different trends. Also, we can see that the infrared colors are often pretty bad. And in fact, the red points at the top represent values that go beyond 400 Kelvin. And we might notice that the V minus R and V minus I and R minus I bands are not great. You see that they're sort of hovering above 0. And then we can sort of go one by one for the different warm stars and the different cool stars to see, as we do this, we can rerun the procedure and get a new median, actually, with all of these remaining colors. And one by one, we eliminate a bunch of warm star colors and a bunch of cool star colors until we're left with 9 warm star colors and 14 cool star colors. So the reason there are more cool star colors is because there's less consistency between the colors. And I expect that is because the models are not as well tested, probably because there are not many people working on these low mass stars. And also they're just tougher to model because of features like line blanketing and molecular lines and whatnot. Why is it? Okay, spoilers. Okay. Okay, so now we're going to actually calculate temperature. We have our warm star set of colors, our cool star set of colors, and I think I forgot to mention this. The cutoff is at V minus K of 7. So warmer than V minus K of 7, or less than V minus K of 7, we use one set of colors. And for the other stars, we use the cool stars colors. And if you might remember, I said that each model spectrum has a temperature, surface gravity, metallicity, and alpha enhancement. We need to figure out all of those to get a final temperature, which we care the most about right now. And to do that, we're going to set 3 of the 4 constant while we calculate the 4th. So once we set the 3, so if I'm getting temperature, for example, once I set surface gravity, metallicity, and alpha enhancement constant, that leaves us with a subset of the models. And we get the difference between the observed and model colors for all those models. Then we use that calculation to see, okay, which spectrum had the best fit, which was the closest match between observed and model colors. So that will correspond to a temperature for each color, and then the mean of those temperatures is going to be our result. But of course, that result may not be at exactly 2200 Kelvin or 2300 Kelvin. Maybe it's at 2237. So when we go through again and we then do surface gravity, we have to pick something on the grid. So we'll pick the closest matching spectrum. So we'll go through this a few times, and we'll do this with the different parameters. And we do this a few times partly because our starting values may not be right. So once we have the temperature, we also need the bolometric flux. And as I mentioned, we're going to use the closest spectrum to what we've found from the temperature result. And we're going to wiggle it a little bit through an iterative method where we apply a polynomial and scale it by the polynomial. Once we're satisfied that because our model magnitudes are within 0.03 magnitudes of our observations, we integrate within the wavelength range and then apply a bolometric correction by figuring out how much flux would be missing from a black body if we only took the same wavelength range from that black body. So then we have flux. We get luminosity by scaling by the parallax, which we then combine luminosity with temperature again to get radius. So we have our radii. How do they fare? So if we compare to interferometry, which is the best way to do it, in my opinion, because you are measuring from the ground and you are literally measuring the size of the star, we match really quite well. So on average, we match within 6.5% of the radii, and about a median of 5.9%, because there's a couple little outliers here. And you might notice the percentages are the same on both plots, right? Our work is on the y-axis, and the interferometric result is on the x-axis, and we have a 1-to-1 line. That's important. So the percentages in each plot are the same because to get angular diameter, you're just scaling the radius by the parallax. So I'm pretty excited that I match better than I could have hoped. Especially the most recent work actually matches better than the older work. So that I'm encouraged by, because you would expect that as time goes on, methods are improved upon, instruments are upgraded, and various things like that. So I'm excited. So then we have radius, we have temperature. We can make a sort of radius HR diagram. And you can see there's a clear main sequence here, which is what I'll be calling it, even though it's radius. And you have young stars at the top in blue and subdwarfs on the bottom in yellow. They stand out really well, except that the some of the young stars blend in. I expect those are stars that aren't very young. And in the white circles, I have the other publications I'm going to be talking about a little later. And so you can see that the trends in this curve actually aren't just like a systematic. I know that there's this like weird thing going on here where things are clumping together. I think the reason for that is that the models are actually very good at those temperatures, and because it's in an interval of 100 Kelvin, and I take the mean result from all the colors, if every color says, oh yeah, it's 3,000 Kelvin, you're going to get 3,000 Kelvin. So I think everything having a very close fit to every color having a close fit to the models results in this. And if I had a finer grid, it wouldn't look quite like that. Oh, I got excited, sorry. All right. We go a lot further than Gaia, which is pretty exciting. So they are cut off all the way down here, only down here, and we get all these other M dwarfs that don't have any fundamental parameters from Gaia. And although it'd be great if Gaia had like a huge amount of definitely vetted, perfect fundamental parameters, because that would be consistent in like a uniform method, they don't. So hopefully this will be very helpful to people who need radii. Can't go to Gaia. All right, so now we can look for our different young star and subdwarf candidates. As I mentioned, the young stars are bigger than the main sequence stars. They hover up here, and again, they blend in a bit with the main sequence. And the subdwarfs are smaller, they're down here, but there's also a very clear dividing line between them and the main sequence. And if I put a line there, you can actually see it. So on this diagram, in the circles, I have young star candidates, and everything below the line is a subdwarf candidate. So the way I figured out the young star candidates is that I used I guess you can't see the slice very well, but I took like a vertical slice of at like a temperature like 100 Kelvin, I think, most of the time, and I took I figured out the median radius of all the main sequence stars in that bin. And then I also got the standard deviation, and I said that any star that has a radius more than 2 standard deviations above that median is a young star candidate. And as I mentioned, subdwarfs are way easier. They're just below the line. And the result of this, one result, is that you can actually you can add radius to the toolbox that you use to identify young stars and subdwarfs. So let's talk a little bit more about how I got the radii. It's a little maybe hard to visualize. So again, remember, I'm going to make a histogram of the radii at just this slice. And it looks like this. You've got the main sequence stars in pink. Subdwarfs stand out pretty well in yellow. And main sequence young stars sometimes stand out, but sometimes don't. And according to that relation I mentioned, I have a region here corresponding to where I would consider something a candidate. So here is the rest of the whole diagram. So the coolest part of the diagram is here, and we go across like this until we get to the warmest stars. So there's a lot of these sort of Gaussian-looking bits in the diagram. So this is how we got the candidates. So we're out of our 1,483 primary stars, we end up with 38 subdwarfs, 1,354 main sequence stars, and 91 young stars. We're being very optimistic. If all the candidates are bona fide, we add 27 of them, and we get these 38 subdwarfs. And again, if we're being extremely optimistic, 55 candidates bring us to this 91 value. So let's move on to trends. You may have noticed that the radii span quite the range over here and not so much over here. What's going on? So you may remember that Garrett Summers visited a few months ago and gave a talk about how star spots affect evolutionary models. He was kind enough to let us use his evolutionary models, which he hasn't published yet. And so that's what I have here. So again, I just have radius and temperature like I've had the whole time, but I have his models here. So they're all, so if you start here, time progresses until you're on the main sequence. And they're all 0.1 solar masses, but the black line corresponds to 0%, and the purple line corresponds to 85% spot coverage. So they're all the same mass, but different spot coverages correspond to different colors. So I could draw a line at the bottom here, where the main sequence is, that sort of give you a sense of, okay, the values, the main sequence values of these stars changes with spot coverage in this trend. You can do the same thing for 0.3 solar masses, and again for 0.5 solar masses. And if you overlay these trends, you see it matches fairly well with what's happening here in the widths of the radius, right? This spans what you expect here, and then it's sort of getting narrower, and then sort of small, possibly because stars aren't actually getting that much bigger due to spots at this mass. So that's pretty cool. Of course, there's going to be other reasons. I know this is probably not the only thing contributing, like metallicity is certainly likely to have something to do with this, along with rapid rotation of some stars, but this is probably playing a substantial role. So another thing that's going on is that there's a change in slope. So there's work by Rabus et al. 2019. The axes are backwards. Let me fix that. All right, he's got these lines, right? So he's fitting all right, let me just, here. Okay, so these are his lines. Sorry. So these are his lines overlaid on my data. So you might have noticed he didn't have as many points as I do. And so that's part of why he probably was like, oh yeah, that was a linear fit. But you might notice, so he says there's a discontinuity here. And he is correlating that with the transition between partial and fully convective energy transfer in stars. And he was saying that happens at 0.2 solar masses. However, our very own Wei-Chun Zhao has identified a gap in the main sequence, which we like to call the Zhao gap, of course, that when he compared to models, found corresponds to this transition. And it happens at 0.35 solar masses. And so I am led to believe that the reason for this is, one, he didn't have enough data, and two, perhaps because the assumption of a linear fit, he was seeing this gap. But so my conclusion is that there's no discontinuity, but rather a transition, and it is not due to the transition between fully and partially radiative energy transfer. In fact, So in fact, there's a very recent publication by Cassisi et al. 2019 that talks about the role of electron degeneracy in the equation of state, which if you haven't thought about what an equation of state is for a long time or at all, it's the relationship between density, pressure, and temperature. So he says that, according to some of the models he was looking at, that electron degeneracy starts to affect the equation of state right around this regime. So perhaps that's what's going on with this change of slope. So now I would like to compare to other people's work. There are 7 other efforts that I'm comparing to. First is Casagrande et al. 2008, who use an Amdorf version of the infrared flux method, which takes a ratio of a monochromatic infrared flux and the total flux to try and get a sense of effective temperature. And there's Tabitha Boyajian 2012, who used the Chara array to get interferometry of M dwarfs and K dwarfs and a bunch of other things. Diederik et al. 2014, again, is the previous version of our procedure. It focused on lower mass stars. Mann et al. 2015 fitted spectra to the BT settle models to get parameters. Filipazzo et al. 2015 used a ton of data across, using spectra and photometry to get as much of a coverage as possible for their luminosities, and then derived radii using ages and evolutionary models, which will be important in a bit. Kessler et al. Did something similar to Mann et al. 2015, but focused on subdwarfs. And Rabus et al., again, is that interferometry work I was talking about with the slope discontinuity, who also used interferometry, but in the southern sky. So I'd like to point out the 2 interferometry papers, and then them combined with Mann et al. 2015, they focused on the warmer stars in our sample predominantly. Then we have Diederik and Filipazzo, who focus on the cooler stars, and Kessler et al., who focus on the cool subdwarfs. So for the next 3 diagrams, I'm going to be comparing my work to their work. So on the y-axis is my result. Whoa. At least it's pretty. Oh, there's a microphone. Please stand by. where'd it go? You see all my notes. Oh, hold on. This is definitely going to cut into my time, and I'm not happy about it. Da, da, da. This is the recap. So far,
The chaos has appeared.
make sure I. All right, cool.
There's order.
Yeah, see, I fixed it. Oh, this is fine. Okay. All right. Now you're awake. Good. Okay, so maybe this is dying. I don't know. Okay. I'm afraid to hit a button. All right, it's okay. Everything's fine. Okay, so on the y-axis is what I got. On the x-axis is what they got. And I have the warm star results from the Mann et al. 2015 and the two interferometry papers on this side, and the cool star results on this side from Filipazzo et al. And Diederik et al. So it's going to be that way for the next three diagrams. I'd like to point out that I actually span the full temperature range. And there's even this little gap here that I filled that people aren't actually doing because they tend to focus on the very coolest stars or the warmer M dwarfs, which are a little easier. So I'm pretty excited I can do this full range of M dwarfs and early L dwarfs. And you may have noticed that this is not very close to the 1-to-1 line. I suspect it has to do with the fact that they use, so again, they get luminosity first, then they get radius using evolutionary models and ages, and then they get temperature by combining those with the Stefan-Boltzmann law. So I suspect that there's something going on with their evolutionary models or ages because those are both really hard to pin down. And I know I'm going to acknowledge that there's a slight underestimation here between what I get and what these others get, but it is within about 100 Kelvin, so I still feel pretty confident that I can trust what I get within the errors. And also, it's hard to pin down what's going on with why this discrepancy is occurring because, as I mentioned, you can get radii somewhat directly with interferometry, and you can get like luminosity somewhat directly by measuring flux from the ground, but you can't really do that with temperature. So I need to do a little more digging to see what's going on with that. On the other hand, other than these couple outliers that I'm going to have to, again, look into before you ask, then my matches to these four works for luminosity are pretty much 1-to-1. I'm only within 7% of Filipazzo for the luminosities, which is good because I expect his result to be of great quality because of how many bands and how many spectra he uses and puts together. Yeah, so I think the fact that all of the data match speaks to the quality of everybody's photometric and spectroscopic data sets. So again, I can compare radius. And once more, we see that I match interferometry very well. And again, the mismatch between Filipazzo's radius and mine is, I think, because of the ages and evolutionary models. So I can also talk a bit, so I've kind of left this work aside because it turns out that you actually need some sort of correction to their method in order to get temperature that makes sense. And I think, as I saw that Mann et al. 2015 described, that the reason for that it has to do with the fact that they're making assumptions that the M dwarfs they're using are in the Rayleigh-Jeans tail, in the wave bands they're using, but they are not. So, and that effect becomes more of a problem for the cooler stars, because you imagine that if you had a black body and you did Wien's law, as you got colder temperature, the peak would happen at further in the infrared. So although this method works well for the hotter stars, I think you need some sort of correction if you're going to use it for the cooler stars. And then there's Kessley et al. 2019, who again is the only one doing the cool subdwarfs. Most of her stars are cool subdwarfs. And strangely, I'm actually, compared to her, my are actually larger. I'm not sure what the difference is. Maybe because, oh, well, I guess I didn't have words there for you. Maybe because something to do with the metallicity. She actually treats metallicity specifically, and I do not do that. So perhaps that has something to do with it. But our radii match pretty well, and our luminosities match pretty well, even though the temperatures aren't quite the same. So kind of a recap and comparison with these methods. What do I have that they don't? Again, Casagrande et al. Make assumptions about the shape of the stellar spectrum, so you need a correction to work with their method. The interferometry efforts, again, you can only use those for the brightest, nearest stars, and very few of those are the M dwarfs. Diederich et al., again, is pretty much this method, but with a few features that are different, such as you have to pick what the colors you want on the spot and pick the spectrum you want on the spot based on those colors. And so that makes it, although it worked very well for what he did, it's not as practical for the large. We would have trouble repeating the results. Although, again, I got fairly similar values, so maybe it's just fine. But again, you can't use it for a large number of stars. Mann et al. Only look at 15 M5 to M7 dwarfs. So the relationships between the colors, the magnitudes, and the fundamental parameters that are reported there are, excellent for stars hotter than that, but aren't as well tested for the colder stars. Again, Filipazzo et al., they depend on the evolutionary models and ages, which are harder to constrain. So although they have really good data, they're limited by that. Gaia, again, only extends to the very beginning of the M dwarf, so you can't really study anything past that with Gaia. Our stars are as small as 0.08 solar radii, which I should have showed you because it's really cool. It's actually 0.08 solar radii to 0.8 solar radii. It's a huge difference. Kessler et al., they also provide relations, but they only go down to M6, and they actually require metallicity, so you would need some sort of measure of metallicity. So in general, what have I got going for me in this procedure? So you only need photometry and astrometry. That cuts down the cost of doing it way down, because you don't need a spectrum, and you can use the small telescopes to get data for your faint stars. And you can also use the established photometric missions, such as Gaia, 2MASS, WISE, Pan-STARRS, and all of these different things. Because it's automated and a uniform method, you can apply it to a large number of stars, and which is very important with missions such as TESS, where there are going to be a large number of stars that have parameters that you want to identify. Again, it spans a large portion of the spectrum because we're going from the optical to mid-infrared. And we're not limited to the 100 Kelvin interval of the grid because of the way we calculate the temperatures. And also, as I've discussed, I think, throughout, it's hard to get down to these coldest stars and really get their values, and we are able to do that despite the complicated spectra, the fact that they're faint, and that they usually have spots. Furthermore, because of the way the procedure is set up, it's easy to add different filters, and you can actually expand it to hotter stars. So moving forward, well, what have we done so far? We have gotten temperatures, luminosities, radii, and radii for lots of stars, and we can do a lot more using just a photometry and a parallax in a uniform, automated, accurate, inexpensive, flexible, multi-wavelength, M0, 2.5, expandable beyond Gaia Tier 2 method. Yeah. We have a catalog of 1,524 stars, which contains their photometry, the astrometry, and the fundamental parameters. We have a very optimistic 25 parsec age population census. And we've noticed a trend in M dwarf radii. The early M dwarfs span a large range of radii, possibly due to spot coverage. And there's a change in slope of mid-M dwarfs that we may be able to tie to the role of electron degeneracy in the equation of state. So what's next? I would like to use Gaia astrometry. As I'm sure you're like, why aren't you using Gaia? We started this before that, and we were working on vetting it, and it just made no sense to update it quite yet. That's next. I also want to look into what's going on with these radii and the different trends we're seeing, how much of it has to do with spots, metallicity, rotation. I'd like to fold in more parameters and see how that changes or enlightens us to what's going on. I would like to use the more recent spectra. I'd like to make some chart observations. So we have angular diameters for a bunch of stars, so now there are some candidates for chart observations. I've got an established version of the code. I'd like to add some more band passes to be able to look at more stars. And then I'd like to look at stars in the TESS and K2 missions. So again, we can provide radii for the exoplanets that are found in the transit. I would like to refine the age candidate criteria. I think that I could do better at that, but this was good for now. And I want to follow up the candidates I do have. And I also got a postdoc, so I'm really excited to do that. Yay! All right, well, I'm not done though. All right, so I'm sure some of you were like, what? We can use Chara, I want to know. So I made a list of stars that can be observed with Chara that I don't think have been done before, because when I was doing this, I looked through the von Braun and Boyajian et al. 2017 review, and then Kane et al. 2017 and Schaefer et al. 2018, and the recent Ravis paper. And none of them had these stars. So maybe there's a publication I missed. But otherwise, I think these have not been done. And so what I have here is, on the y-axis, I have angular diameter in arcseconds, milliarcseconds, and apparent magnitude. All of these stars are of magnitude 14 or brighter, and are of angular diameter 0.5 arcseconds, or less. I think that's right. And I have, so in blue they're all the same stars. So the blue is the R-band data, and the red is the H-band data, because PAVO works in R-band, and Classic works in H-band, the two instruments on the interferometer. And then I have this box here in green corresponding to what can be observed by PAVO, and a box here in yellow for what can be observed in Classic. So these blue boxed points can be observed by PAVO, but they are actually stars that have already been done. And all these red circled points can be done by Classic. So again, these are the ones that haven't been done. So go forth. All right, so then I got a postdoc, and that's going to enable me to do some of these things, hopefully all of them. That'd be pretty cool. So the idea, though, is that I'm going to combine my radii with analysis of test data and K2 data for tens of thousands of stars within 100 parsecs. And what I want to know is how the magnetic activity of the stars affect the planets. And so I'm going to relate like the size of the star and the magnetic activity to figure out more about how the radius and the magnetic activity of the star relate, and then also how that magnetic activity is affecting the sizes of the stars. Because again, they're transiting planets. I'll have the size of the star, get the size of the planet. And you may have heard about something called the Fulton gap. And for sun-like stars, there's like a bunch of radii that you don't see planets of a certain radius, just not nearly as much as the other ones. And so that they think might be from magnetic activity. And so maybe I can find one for the M dwarfs, different M dwarf Fulton gap. So that's what I'm going to do. I'm pretty excited. And thank you all for listening.